Well, we'd like to present to you guys question representation in mapping in transformers, or KERMIT. So, a quick overview of the problem. We're dealing with an area called question and answering systems in natural language processing. So very briefly, question and answering involves a passage with some context, and then a question about the passage or context, and then an answer. Most importantly, the answer is taken from the passage word for word. This is an objective assessment of reading comprehension skills for AI and machine learning models. The current best performer is BERT, or bidirectional encoder representations from transformers. This was able to achieve state-of-the-art performance, not only on question answering, but also in 11 separate NLP tasks as well. Our specific question answering task here is using the Stanford Question and Answer Dataset version 2.0, or SQUAD. The difference between SQUAD version 2.0 and 1.0 is that SQUAD 2.0 is more difficult because it has questions that do not have an answer, just as the example given on the screen. As of February 2019, all of the top 10 models on the official leaderboard utilize BERT in some manner. And then our data set has 130,000 examples as training data. We'd also like to point out that the training data that we were provided is slightly different from the official training data if you're trying to reproduce our results. So our approach, we started with looking at what does BERT do, how does BERT predict start and end tokens. So BERT uses only the context final hidden layer during the fine-tuning phase. We believe that this does not allow BERT to focus as much on the question representation. While theoretically BERT is able to map some of the question onto the context token by doing pre-training and fine-tuning using its transformer layers, we believe that a more direct mapping from the question representation should help performance, especially in SQUAD version 2.0 where there's a lot of no-answer questions. To do this, we propose various methods. The first one is CNN. We have tried two versions of the CNN. Version 1, we got inspiration from character embedding models. This is a very basic CNN as shown in the image. For CNN version 2, it's slightly more complex. We use 4 region sizes, so 2, 3, 4, and 5. Idea here is to focus on shorter versus longer phrases in the question. And then for the output, we notably do a 4 max pool with stride length of 4. This was done so that when we concatenate the outputs of these 4 filters, we get back a feature vector of the same length.
BERT is also known to capture all the meaning of the question, the CLS token of its sequence. So we tried using that, and another method we tried was max pool, where we take the max pool between all the question representation vectors. We also tried different methods for mapping. First was skip connection, where we do an element-wise multiplication of the question representation onto the context, and then feeding forward the original context token representation. Another method that we tried was concatenating the question representation and the context representation and adding additional layers to better capture the question into the context. We also tried different things, such as using BERT as feature vectors. BiDef was the previous best model before the invention of PCEs. So we had to ask, how would its performance change if you replaced its word embeddings of glove with BERT and also including character embeddings? We were surprised that our character embedding and BERT model actually worsened in performance over time.
Other methods we tried include data augmentation. This involves using other data sets such as Trivia QA and Wiki QA during the fine-tuning phase to improve the performance of BERT. For future work, we also propose different ways of generating synthetic SQUAD data. For example, using seek-to-seek models to generate questions and answers, or using part-of-speech tagging to identify, for example, nouns or verbs in the questions and replacing them with random nouns and verbs to generate strong negative synthetic training examples. As for results, the first 2 lines show the baseline BiDef model and the baseline BERT large uncased model. During our experiments, we found the importance of when fine-tuning BERT to fine-tune the entire model and not just the final fine-tuning layer. We found that when you freeze the pre-training embeddings, performance suffers dramatically. And then our best model was achieved by tuning the hyperparameters of the original BERT model, most notably max sequence length, max query length, and max answer length. This allowed us to get second place on the dev class leaderboard.
We analyzed the results of our model to understand where we can improve. We first found examples where if there were dissimilarity between words, that the model still answered where there were no answers. We believe that an improvement to this could be by incorporating word embeddings from glove during the pre-training process of BERT. And our second improvement idea is also tying back to our negative synthetic data idea of generating more examples where there are no answers. Our second idea of improving BERT was also understanding better sentence structure and constituency parsing. We saw that if the question had an unconventional structure, that our model had struggled. An improvement to this could be having an architectural change of BERT by feed-forwarding diagnostic classifiers and understanding part of speech and dependencies better. And we could also improve the model by having more diverse training. We have three conclusions. First is that BERT is inflexible. Our experiment with different Kermit models showed that BERT actually worsened in performance. And furthermore, using BERT PCEs as the hidden states for BiDef did the same. Our second conclusion is that for best outcome, we shouldn't modify the baseline architecture at all. In fact, our best model, which ranked second in class, was just through hyperparameter tuning. This is also representative of the actual leadership leaderboard of Squad 2.0, where the top two leaders use synthetic data and n-gram masking on top of the original BERT model. We recommend future work in understanding how to better ensemble BERT's architecture and better understand how to utilize BERT's PCEs, because pre-training everything is a very computationally expensive task. Thank you.